Okay, so we will start now. In the last lecture of electrical and hybrid vehicles, we have seen some fundamentals of electric vehicle as well as gasoline powered engine vehicle, right? So in the last session of lecture, we have seen the characteristics of power plant, characteristics of the transmission, and we have started with the vehicle performance, right? So talking about the characteristics, then we have seen the ideal characteristics which is required. Okay, so in case of power versus speed characteristics, the ideal characteristic would be like this, right? Power remains almost constant over the entire speed range, right? And then we have seen the torque speed characteristics also, right? So in torque speed characteristics, what we have observed? We have observed that initially when the speed is low, at that time torque remains somewhat constant, and after that torque will decrease hyperbolically with advancement in the speed. Okay. So if any power plant gives you the characteristics similar to this, then this is the ideal one. Okay, it will give you the maximum performance of the vehicle, right? And we have compared the IC engine as well as electric vehicle, electrical motor as an power plant, and we have seen that in both the cases we will be able to get the shape of the characteristics just like that. The only difference is in case of gasoline powered IC engine, we have seen that we have to use the multi-gear transmission, right? So what we have done is we have seen that the first gear will give you this kind of characteristics, then we will have a second gear, then third gear and fourth gear. Okay, so this will give you this kind of characteristics. And in case of electrical motor, we are getting the same characteristics, right? Almost same like this. So both are valuable. Whenever you want to get the maximum performance of the vehicle out of the vehicle, then IC engine is also preferable as well as electrical motor is also preferable, right? But we have seen some differences between this electrical vehicle as well as IC engine vehicle. We have seen a lot of differences, and then we have decided that the electrical vehicles are somewhat beneficial now, as the main reason behind this is the zero emission vehicle. It is a zero emission vehicle. No pollution is there at all. Right? After that, we have started with the vehicle performance, right? And we have seen that the performance of vehicle is described by its maximum cruising speed, gradability, and acceleration. Okay, so we have seen the prediction of vehicle performance, which is based on the relationship between the tractive effort and the vehicle speed, and that is what we have seen in the previous lectures, right? And in the last lecture we have derived one equation for maximum speed of the vehicle, which is given by V max is equal to pi np max rd, d will be at suffix rd upon 30 I0 Ig minimum, right? Where we have seen this NP max is the maximum speed of the engine and Ig minimum is the minimum gear ratio of the transmission, right? So that was our equation which will give us the maximum speed of a vehicle. Then we have seen the gradability. Okay, so whenever you want to define the gradability, it is nothing but a grade that the vehicle can overcome at a certain speed. What do you mean grade? Grade is nothing but an angle. You can also call it a grade angle. Okay, so this is a grade angle that the vehicle can overcome at certain constant speed, right? And for heavy vehicle, heavy commercial vehicle, or you can say off-road vehicles, the gradability is usually defined as the maximum grade or grade angle in the whole speed range. Okay, and we have seen how to find out this gradability. It is being given by sin alpha equal to d minus fr square root of 1 minus d square plus fr square O1 over 1 plus fr square. Okay. So this is the equation with which we will be able to find out the gradability of a vehicle, right? And then there was the third parameter, which is acceleration performance, right? So how will you define this acceleration performance, right? When we talk about the acceleration performance of a vehicle, it is usually described by its acceleration time and the distance covered from the zero speed to a certain high speed. Okay, say for example, I am taking 0 to 50, how much time it will take to reach 50 kilometer per hour speed or 100 kilometer per hour speed, right? So that was the performance, which is acceleration performance, right? And we have seen that we are using the for a dynamic equation, we are using Newton's second law, right? And what it states, we have seen this equation, mv dv by dt is given by ftf plus ftr. Okay, this is my total tractive effort, right? This term is nothing but total tractive effort, right? And this total tractive effort is to be subtracted from the total resistance. Okay, so whatever resistance we are having, we will sum up all these resistances, say ff, frf, frr, then aerodynamic drag is also there, then grade resistance is also there, right? So the second term of this left hand side of the equation, right hand side of the equation, is nothing but it represents the vehicle resistance. Okay, so this was the dynamic equation of a vehicle which we have seen, right? Now from this equation, suppose I want to find out the acceleration of the vehicle, right? Then you may write down acceleration of vehicle is given by small a, which is nothing but dv by dt, right? So it will be equal to ft minus ff minus fw. This is tractive effort, this is the resistances, divided by mv delta, right? Here delta is the mass factor which we already have seen. Okay, now put the values of this ft, ff and fw. All we know, ft is the total tractive effort, that was tp I0 ig eta t by rd, okay, which minus ff is mv into g time fr, mvg fr, and aerodynamic drag is given by 1 by 2 rho a cd af v square, okay, and this is to be divided by mv delta. Okay, so you can simplify this equation in this particular fashion, that g by delta into d minus fr. Okay, call it equation number 4. Okay, so in this equation, delta, as we know, it is nothing but the mass factor. Okay, and we are taking this mass factor considering the equivalent mass increase due to the angular moments of the rotating components. Okay, so this mass factor delta can be written as delta is equal to 1 plus IW upon MVRD square. Okay, again we are taking the direct equation. We are not interested in deriving this equation or knowing how this equation is there. Okay, this is the concern of automobile engineers. So we will be directly using this relationship of delta. Okay. So here, if we see delta is equal to 1 plus IW upon MV RD square, where this IW is the total angular moment of the wheels, right? And IP is the total angular moment of the rotating components which are associated with the power plant. Okay. So now the calculation of the mass factor delta requires knowing the values of the mass moment of inertia of all the rotating parts. Right? In the case where these values are not known, then the mass factor delta for a passenger car could be estimated using some empirical relations. Okay, when we don't know this much of parameters I0, IG, IP, specifically IW and IP. Okay, what was there IW? If I talk about this IW, it was total angular moment of the wheels, right? And IP is total angular moment of the rotating components. Total angular moment of the rotating components which are associated with the power plant. Associated with power plant. Okay. So this is the case when we know this IW and IP. Okay, then we will be able to find out the mass factor delta. But suppose we don't have this value, we are not knowing this value, still we need to find out the mass factor. Then we are going to use this empirical formula to find out the delta, which is given by 1 plus delta 1 plus delta 2 Ig square I0 square. Right? So here I have these two terms, delta 1 and delta 10. Okay, so this delta 1 represents the second term on the right hand side of the equation, that is this equation, equation number 5. Okay, so I am talking about this term, IW upon MV RD square. Okay, so this is the delta 1. Okay, and the reasonable estimate value of this is 0.04. Right? And when we talk about delta 2, right, this delta 2 represents the effect of the power plant associated rotating parts, and this has a reasonable estimate value of 0.0025, right? So we don't know the values of this IW and IP, but still if we are using this empirical formula, then we will be using this delta 1 equal to 0.04 and delta 2 is equal to 0.0025. Okay, then Ig and I0 are again grids that we know. Okay, so we will be available with this particular thing, right? So now we know how we will be able to find out the acceleration performance of the vehicle, right? And if we try to see this performance of vehicle in terms of acceleration, then we will try to compare the acceleration of a gasoline engine powered vehicle with the 4-gear transmission and acceleration of an electric machine powered vehicle with single gear transmission. And let us see what is the difference. Okay, so now we will try to plot the speed versus acceleration. Okay, so on the horizontal axis we will be taking speed of the vehicle, in kilometer per hour, and on the vertical axis we will consider acceleration, which is meter per second square, right? And same we will plot for the electric powered vehicle also, right? So speed is there and acceleration will be there. Okay. Now we know whenever we talk about the acceleration of a gasoline engine powered vehicle, then we are available with the 4-gear transmission. Okay, so we need to consider each and every gear. Okay, say for first gear, okay, just let me have some values first. Okay, this is my 0 speed, 50, 100, 150 and 200. Similarly, acceleration will be 1, 2, 3 and 4. Here also we'll consider the same scale. Right. So now if I talk about the gasoline powered engine, right, then we are talking about the first gear. Okay. So in case of first gear, we will have this kind of characteristics. In case of second gear, this will be the characteristics. In case of third gear, now characteristics will become somewhat flat like this. Right. So this will be the characteristics for first gear, second gear, third gear and fourth gear. Okay. And if I talk about the acceleration of an electric machine powered vehicle, and in that case we see the transmission may be single gear or double gear. Okay. So considering single gear transmission, we will have this kind of characteristics. Okay. Not a straight line, it will have some hyperbolically decreases hyperbolically like this. Okay. So these are my two typical cases which we have considered. Okay. So this is the acceleration of gasoline powered vehicle with 4-gear transmission. Right. And second one is for acceleration of an electric machine powered vehicle with single gear transmission. Right. So these are the things. Right. Now we have this equation of acceleration. If we go back to this equation number 4, a is equal to dv by dt, right? So from this equation, the acceleration time ta and the distance say sa from low speed v1 to high speed v2, that is what we try to do. Okay, because we have the equation of acceleration. Now what do you mean by acceleration performance? That in how much time it will cover some of the distance. Okay, so the we are interested in deriving the acceleration time as well as the time distance traveled within that particular time. Say my lowest speed is v1 and now I am reaching in some time ta to another speed v2. Okay, so how will you find out that acceleration time, right? So we will integrate the equation of acceleration, right? That is nothing but we will try to integrate it over a range of v1 to v2, right? So here acceleration time ta is integration v1 to v2 mv delta v upon tp ig I0 eta t by rd minus mvgfr minus aerodynamic drag half rho a cd af v square into dv. Okay, so this is our acceleration time. Similarly, you will be find out the distance. Distance say SA, right? So distance SA is nothing but integration v1 to v2 mv delta tp ig I0 eta t divided by rd minus mvgfr minus drag rho a half rho a cd af v square dv. Okay, so this will be my equation number 7 and equation number 8. Equation 7 and equation 8. Okay, acceleration time and the distance. Okay, so in this equation number 7 and equation number 8, the torque of the power plant TP, you can see. Okay, I'm talking about this term TP, which is nothing but it represents the torque of the power plant, right? So this torque of the power plant is the function of speed, okay, which in turn is a function of vehicle speed and the gear ratio of the transmission. And this makes it difficult to solve these two equations, equation number 7 and equation number 8 analytically. And therefore, we will use numeral methods. Okay, so generally, numeral methods are used to find out the acceleration time and distance traveled. Okay, so we will see some figure which will shows the acceleration time and the distance along with the vehicle speed for both the cases, for a gasoline engine powered and an electric machine powered electric vehicle. Okay, such that we will get some idea of the time as well as the distance, right? So now let us say we will use one for gasoline powered engine vehicle and another one for electric powered vehicle. Okay, so here again we will consider our vehicle speed in kilometer per hour, right? Then on this I will use acceleration time. Okay, this is my acceleration time in second, and on this axis I will take acceleration distance in meter. Okay, same is the case over here. This is 0, 50, 100 and 150. This is representing distance in meter. And this is representing acceleration time in second. Acceleration time in second. Okay. Now talking about the characteristics. Okay. Time characteristics. First we will take. So vehicle speed versus time in case of gasoline powered vehicle. So we will get some this kind of characteristics. Right. And if I talk about distance traveled, then this will be like this. Okay, so this is the typical characteristics. Okay, the one with green line shows the time, and the red line will shows the distance. Okay, this is representing time. Okay, now compare this with the electric vehicle. Okay, so in case of electric vehicle, whenever I talk about the time, then the time curve will be like this. And if I talk about the distance traveled, then it will be like this. Okay. So this is representing distance, and the one with green line represents the time. So when you compare these two, now you can see, okay, we are getting very smooth curve in case of electrical vehicle. Okay, so this is also one of the advantage of electric vehicle. We can consider it as an advantage of electric vehicle. Okay, so this particular figure shows the acceleration time and distance along with vehicle speed. Okay, for a gasoline powered or say IC engine or electric vehicle. Okay, so this is how we will be able to predict the acceleration performance. Nothing but the acceleration time and the distance which is covered from zero speed to a certain high speed. Okay, so whatever parameters are required to identify this, all the parameters, all the equations are now available to us. Okay, so we'll be easily predict the acceleration performance now. Okay, so these three were the parameters which will help us to find out the vehicle performance. Right, that is what we need to know. Right, now after this vehicle performance, the main thing you need to know, once our vehicle has been accelerated, what will happen? Whenever we are under traffic conditions at that time, frequently we need to apply brakes. Okay, specifically whenever we are driving our vehicle in the city area, right? If you are on the highway, then braking will be needed for very small time, not frequently. But whenever we are in a dense area, we are traveling our vehicle in the dense area, at that time frequent braking will be required. Okay, so it is necessary for each and every design engineer while designing the vehicle, whether it is IC engine vehicle or electrical vehicle, that it should focus on the braking performance of the electric vehicle. Okay, it is very much necessary because whenever we are applying the braking at that time, how will be the distribution of braking on the axles also? Okay, we are having the front axles and rear axles. What will be the braking force? That is also important, right? So these are the two parameters which we need to consider while considering the braking performance. Okay, so we will quickly go through the braking performance of the vehicles. So my next topic is braking performance. Okay, so it is undoubtedly one of the most important characteristics that affect the vehicle safety also. Okay, in urban driving, a significant amount of energy is going to be consumed in braking. Okay, so in recent years, more and more electric drives have been evolved in vehicle traction, such as electric vehicles, hybrid electric vehicles, and fuel cell powered vehicles. Okay, so the electrification of the vehicle drivetrain makes it feasible to recover some of the energy which is lost in the braking. Okay, and this technology is usually referred to as regenerative braking, right? So if we have a well designed regenerative braking system, then it will not only improve the vehicle performance but also potentially improves the braking performance. Okay, so in this particular section we will see a method of approach to the analysis of braking performance, right, which aims to help the designing of regenerative braking system. Okay, so it is much necessary whenever we do apply braking. Suppose your vehicle is running at 70-80 kilometer per hour, right, and suddenly we need to stop the vehicle. Okay, wait a minute. Pardon for the interruption. Okay, so we are talking about this braking performance and specifically regenerative braking. So I was telling you that whenever we are running our vehicle at say some 50 or 60 kilometer per hour, and suddenly when I apply braking, what is going to happen? This vehicle is having its own kinetic energy. Okay, so all the kinetic energy is going to waste if we are not using this. Okay, and somehow if we manage to use the kinetic energy of the vehicle, then it will help us to charge the battery. Okay, so what is happening, whatever power is we are drawing from the power plant, we must be able to give some power back to the power plant or use that power to charge the batteries. Okay, so whatever amount of power we are able to use, that is called regenerative capability. Okay, so that is why in most of the vehicles now regenerative braking is used. Okay, and to understand the braking performance very well, we require to understand the braking force and braking distribution in the axles. Okay, so we'll start with the first parameter, which is the braking force. Okay, so to understand the braking force, let us have a simple figure of the wheel. Okay, so suppose this is my vehicle wheel, right, and this is our ground level over there. Okay, So this blue line shows the level of the ground. Okay, and this will be our radius of the wheel, RD. Now what will happen? There is one pressure which is acting downward. Okay, let us say this pressure be P. Okay, it is nothing but a normal load, right? And our wheel is rotating with angular velocity of omega. Okay, and this is my velocity of the vehicle B, right? And this is my origin, say 0A. Now what is happening? Whenever we do apply braking, what is going to happen? That is what we are interested in. Okay, so when the brake pad is pressed against the brake plate, what is going to happen? It will develop a frictional torque on the brake plate. Okay, and this braking torque will result in a braking force in the tire ground contact area. Okay, it is just this braking force that tries to stop the vehicle. Okay, and this braking force can be expressed as, now whenever we do apply the braking force, what is going to happen? There will be a torque which will act against the speed of the vehicle. Okay, so say here, this is the force acting in this direction, say TB, braking torque. I am talking about the braking torque, and this braking torque will try to stop the vehicle, right? So if I talk about the braking force now, then this braking force FB is given by braking torque by the radius, that is RD. Okay, so this is how braking force has been produced, right? Now this braking force increases with increasing the braking torque, right? If TB increases, then FB is going to increase. However, when the braking force reaches the maximum braking force that the tire ground adhesion can support, it will not increase further, although the braking torque may still increase. Okay, so what will happen? See, if we try to understand this with the help of the diagram, then it is very well understood. See, on the horizontal axis, I am talking about the braking torque, and on the vertical axis, let us say we are having a force, braking force, right? So what is going to happen whenever braking torque is increasing? As I have told you, according to equation number 1, if TB increases, then FB is going to increase, right? Like this. But what will happen when braking torque reaches a certain value? After that, what is going to braking force reaches to certain value, after that what is going to happen? This braking force is not going to increase, still my braking torque is increasing. Okay, so we will have some forced value. Okay, so this is my maximum braking force. Okay, so this maximum braking force is limited by the adhesive capability, which is expressed as, if I talk about now FB max, then this FB max is given by mu B into W, right? So here this mu B is adhesive coefficient of the tire ground contact. Adhesive coefficient of tire ground contact, right? Okay, so the adhesive coefficient is varying with the slipping of the tire, and there exists a maximum value in the slip which is in the range of 15 to 20%, right? And it is declining somewhat at 100% of the slip. Okay, so this will be the maximum braking force that can be achieved, and this will be the normal braking force. Okay, so as the braking torque increases, braking force will increase up to certain value when it becomes FB max. Why it reaches to the maximum value? Because This will be the maximum force that the tire ground adhesion can support. After that, the wheel will slip, right? That is what we have seen, right? So this is the braking force, right? Now, after braking force, you need to understand the braking distribution. Okay, so the second parameter is braking distribution on front and rear axles. Okay. So to understand this, first let me try to draw one figure. Okay, so we will have one car once again. This is our distance. This is my car. Okay. So this represents the center of the vehicle on front axle and rear axle, right? So now, if I am talking about the total length between these two axes, center of the axis, then it will be L. That is what we have seen, right? So here, let us say this is the force, braking force, which we are applying. Okay, the braking force applied at front vehicle, let it be FBF, and braking force applied at the rear axle is say FBR. Okay, then let us have these two set. Okay, now this is shows the distance L, right? And let us say this is my one center. Okay, this component represents MVJ, and this is due to gravitational force, that is mv into g. Okay, so this particular length, oh sorry, yeah, okay, so this point, this is length LA, and this will be length LB. And if I talk about the ground clearance, okay, this is our ground clearance, then this will be my height HG. Okay, so these are the different forces acting on a vehicle during braking, and we are considering the flat road only. Okay, I am not going up a grade or going down a grade. Okay, so this is the force acting on a vehicle during braking, of course on a flat road, right? Okay, so this is FWR. Let us say this is my axle A and axle B. So now this figure shows the forces acting on a vehicle during the braking on a flat road, right? So we have rolling resistances and aerodynamic brake. These are ignored in this particular case. Okay, we have ignored the rolling resistance, we have ignored the aerodynamic brake. Okay, because they will be quite small compared to the braking forces. Okay, so here I have used one term mv times j. So j is the deceleration of the vehicle during braking. Okay, and it can be expressed as j equal to fbf plus fbr divided by mv. Okay, this is my deceleration of vehicle during braking, of course. Okay, so here fbf and fbr, these are the braking forces acting on front and rear wheel respectively. Okay, so the maximum braking force which is limited by the tire ground adhesion, and it is proportional to the normal load acting on the tire. So the actual braking force developed by the brake torque should also be proportional to the normal load, so that both the front and rear wheels obtain their maximum braking force at the same time. Okay. So during braking, what happens? There is a load transfer from the rear axle to the front axle. Okay. So by considering the equilibrium of moments about the front and rear tire ground contact points A and B, the normal load on the front and rear axles, let us say WF and WR. Okay. So here, this is my WF and this is my W, right? So what will be the value now of this WF? Okay, so it should be equal to mvg divided by L into LB plus hg into j by g, and for rear wheel it will be mvg by L LA minus hg into j by g. Okay, so here j is deceleration of the vehicle, right? So the braking force of the front and rear axle should be proportional to their normal load. Okay, and hence we will obtain fbf upon fbr is equal to wf upon wr. Okay, so it will give you lb plus hgj by g upon LA minus hgj by g. So these are the equations which will be useful to us. Okay, so in vehicle design, the actual braking forces on the front and rear axles are usually designed to have a fixed linear proportion, and this proportion represented by the ratio of the front axle braking force to the total braking force of the vehicle. Okay, so while designing the vehicle, we need to take care of this thing, and let us say this is beta. Okay, so beta will be equal to fbf upon fb. Okay, what is it? It is the actual braking force on the front and rear axles, and these are designed to have a fixed linear proportion. Okay, so this is the proportion which is represented by the ratio of front axle braking force to the total braking force. Okay, so here fb is my total braking force of the vehicle, and beta being the actual braking force on the front and rear axle. So it can be represented as fbf equal to beta times fb. Okay, this is one thing, and for rear wheel it will be fbr is equal to 1 minus beta times fb. Okay, so these are our equation of interest. Okay, so now we know fbf and fbr. Okay, so if we take the ratio of this fbf and fbr, then it will be equal to beta upon 1 minus beta, right? So this is what we have in case of braking. Okay, so during braking on the roads with an adhesive coefficient that is less than say mu0, right? So what will happen? The front wheel locks up first, whereas when the road adhesive coefficient is larger than mu0, then the rear wheel locks up first. Okay, so when the rear wheel locks up first, the vehicle will lose directional stability. Okay, that is what happens. Now, if some slight lateral movement of the rail wheels is initiated by side wind or road camber or some centrifugal force or some yawing moment due to the inertial force about the center of the front axle, that will develop. Okay. So the lockup of the front wheel will cause a loss of directional control and the driver will no longer be able to exercise the effective steering. And it should be pointed out, however, that front wheel lockup does not cause directional instability. This is because whenever the lateral movement of the front wheel occurs, a self-correcting moment due to the inertial force of the vehicle about the yaw center of the rear axle develops, and consequently it tends to bring the vehicle back to a straight line path. Okay. So the loss of steering control may be detected more readily by the driver and control may be regained by the release or partial release of the brakes. And contrary to the case of front wheel lockup, when rear wheels lock and the angular deviation of the wheel exceeds a certain level, control cannot be regained even by complete release of the brakes and by the most skillful driving. Okay. So we suggest that the rear wheel lockup is more critical situation, particularly on a road with a low adhesive coefficient. Okay, since on a slippery surfaces, the value of the braking force is low, the kinetic energy of the vehicle will dissipate at a low rate and vehicle will experience a serious loss of directional stability over a considerable distance. Okay, therefore, designers of the vehicle brake systems must ensure that rear wheel do not lock up first. Okay, and we have seen nowadays ABS systems are there, which is anti-lock braking system. Okay, so the anti-lock braking system developed in recent years can effectively prevent wheels from locking up. Okay, and this system employs speed sensors to detect the wheel rotating speed. When a wheel lockup is detected, the braking pressure control system reduces the pressure and brings the wheel back to its rotation. Okay, so this is how our braking system works. Okay, and we will be able to predict the performance of this braking with the help of the braking force and distribution of braking on the front and rear axles. Okay, so we have some equations which might be useful to us to predict the performance of the braking. Okay, so we shall stop here for today. In the next lecture we will continue with this topic. Okay, if you have any question, then you can ask.